All right. Today, we're going to learn the last test. Last two tests, actually. Okay? We're going to learn the so-called ratio and root test. I will give you an idea as to why these tests happen to work. And it turns out that both of them have something to do with geometric series. And the reason that they work at all is because of what we learned about as it pertains to geometric series. I think you'll see what I mean once we start getting into the details here. But let me see. Oops, what is this saying? Okay, here we go. Ratio and root test. Let's do it. Oops. Okay, again, the last test we did the alternating series test, and that was the first time we really thought carefully about having series with potentially negative terms in them. Yes? Now, that's not to say there wasn't a test before that could deal with series with negative terms. Like, what test did I say you could use? The what? Limit comparison test. Limit comparison test applies across the board, okay? So limit comparison test you can apply flat out in any situation with no apology whatsoever, okay? Alternating series test deals with a specific kind of series that has negative and positive terms every other, yes? The ratio and root test is a little bit more lenient. It applies to any situation whatsoever, sort of like limit comparison, okay? Ratio and root tests are another example of something that we can apply across the board without apology, whether it's a series of positive terms or not, okay? So again, the plan is to talk about the ratio test first, and then we will talk about the root test, okay? And it turns out that one of these two tests is more powerful than the other. All right? So it turns out that actually the root test is the most powerful of the two tests. Okay? Turns out anytime the ratio test would have told you something, the root test would also have told you something. But in order to see that, you would have to know things like Stirling's approximation. Remember I told you that like there are cases where limit comparison seems to break down, you know, because you don't know exactly how like n factorial behaves or something. But if you know something like Stirling's approximation, it turns out that you can just use limit comparison all the time. Okay, but with Stirling's approximation for factorials in your back pocket, it turns out that the root test it supersedes the ratio test. Does that make sense? But sometimes the ratio test is actually a little bit more convenient to use anyways. Okay? All right. So one thing I want to point out is that the ratio test is particularly useful in the case where you have factorials and exponentials. Okay? Factorials and exponentials. So notice that the application of the ratio test does not just restrict us to series with positive terms. It says, let series AN be a series with non-zero terms. Well, hello, that just means that I have stuff that's that's non-zero, yes? That means I could have some terms being negative, some being positive, etc. Okay, and notice what number 1 says. Okay, just in light of some of the things we've been doing here. Oops, let's see, yeah. It says, why is this thing not working? Come on now. There it is. I think it recognizes this thing now, hopefully. There we go. Thank you very much. Series converges how? Absolutely. When the limit of consecutive terms goes to a number less than 1. Does that make sense? You take the ratio of consecutive terms and you take that limit And if you get something less than 1, you're good to go. Now, you might ask me, why on earth would that be important? Well, basically what this says is that the terms are getting, what do you think? So if I take the next term over the current term, and I take that ratio, and I take the limit, and I get something smaller than 1, what is that telling us about the terms? What's happening to the terms? They're getting smaller. Do you know what I'm saying? They're getting smaller, and they're getting smaller actually fairly quickly in order for this to happen. Okay? So for instance, suppose that this was equal to 1/2. Okay? Which is clearly less than 1. Suppose it was equal to 1/2. Well, that would mean that for n large, right? For n large, what would be going on? Well, the absolute value of an plus 1 over an would be roughly equal to 1/2. Does that make sense? Yeah? And so that would mean that the absolute value of an plus 1, the next term would be how much of the previous term? Think about it, just kind of solve this algebraically. Then the next term would be how much of the previous term? Half of it. Half of the absolute value of an. Now, can you think of things where that sort of situation happens, where the next term is like half of the previous term? Can you think of a series where something like that happens? This isn't a trick question. Can you think of a situation where the next term is like half of the previous term? Yeah. Like a geometric, like where, it's like 1 plus a half. That half is half of the previous term. Does that make sense? If the previous term was 1 plus a fourth, how does a fourth relate to 1/2? It's half of it, yeah? Plus an eighth. How does an eighth relate to a fourth? It's half of it. So this right here, I just want to point out that this relationship says that the series behaves like what? Series behaves like a geometric. Like a geometric with ratio r less than 1. Basically, does that make sense? Because in this case, 1/2 would be like the ratio. Does that make sense? So essentially, this limit is like the ratio. Okay, what's eventually happening is the next term is like some common ratio times the previous term. That's what it's behaving like eventually. So the series behaves like a geometric series. And what do we need to be true about the common ratio in order to guarantee convergence? It needs to be less than 1. Does that make sense? Common ratio needs to be less than 1. So that's why we put this little requirement on here. And it converges absolutely, which means even if I were to put absolute values in here, the thing would still converge. Does that make sense? And that's because it is behaving like a geometric. So even if I had like some negative terms in there, yes, it would still be like, -1/2 times the previous term or something like that. So it would still converge in absolute value, okay? So once again, the thing I want you to keep in mind is that what is happening with this test is you're noticing that the thing is behaving like a geometric series. Eventually, that's what's basically happening, okay? And the series diverges if the limit is bigger than 1 or the limit is like infinity. But come on, are you kidding me? If the limit is bigger than 1, what is that telling you about the terms? They're actually getting bigger, which is just ridiculous. Does that make sense? The terms are getting bigger, of course the thing is going to diverge, right? So first, if the limit of the ratio, by the way, you're taking absolute values here, okay? If the limit of the ratio of absolute value of terms is less than 1, you have convergence because the thing's behaving like a geometric. If the limit of the ratio of or absolute value of the ratio of consecutive terms is bigger than 1, the series diverges, and of course that had to be true because that means the terms are actually getting bigger, which is a horrible situation to find yourself in, yeah? And finally, if the limit of the ratio of consecutive terms is exactly 1, then you don't know. You don't know what's going on, okay? You can't make a conclusion. There are situations where you have convergence, and there are situations where you have divergence. So for example, the reason it's inconclusive is, let me just show you a quick example. So what about series 1 over n? Okay, in this case, you know, my an, right? My an is just 1 over n, yes? So what would an plus 1 equal? If an is 1 over n, what's an plus 1? That means the next term. 1 over n plus 1. So what about the absolute value of an plus 1 over an? Well, that's going to be 1 over n plus 1 divided by 1 over n, which, by the way, if I kind of invert the bottom, this is like n over n plus 1. Yes? And what does that go to as n goes to infinity? That goes to 1. As n goes to infinity, this goes to 1. And what's true about this series, just to make sure we're all on the same page here? What's true about this series? This thing diverges, yes? So this is a diverging series. This diverges. That's the harmonic series. But on the other hand, let's look at a different series. How about this one? How about series 1 over n squared? Okay? Then in this case, what's an? What's an in this case? Well, it's 1 over n squared, yeah? So an plus 1, what would an plus 1 be? 1 over the quantity n plus 1 squared, yeah? So if you look at the ratio of consecutive terms, I am telling you it's going to be 1 over the quantity n plus 1 squared divided by 1 over n squared, which is n squared over the quantity n plus 1 squared. And what do you think that goes to as n goes to infinity? Think about it. If I were to multiply out the bottom, it would be n squared plus 2n plus 1. But I would have n squared over like n squared. What does that go to? 1. And yet, what's true about this series? What do we know is true about this series? This thing converges. Right? Right? We have the harmonic series, or p series of p equal to 1 in the first case, and then we have a p series of p equal to 2 in the second case. In each one of these cases, the ratio of consecutive terms had limit 1, correct? In the one case, we have divergence. In the other case, we have convergence, which tells us that we can't conclude anything in the case where the ratio goes to 1. Does that make sense? Am I making sense here? Hopefully. Okay. So questions on that? Questions on sort of the specifics of the ratio test? And again, I want to reiterate to you that the factorial situation and the exponential situation are particularly pertinent in this case. So once again, what's the reasoning for why we have convergence when the ratio of consecutive terms goes to something less than 1? What's the series behaving like? A geometric. Yes, that's the rationale. Okay. And in the second case, of course, that diverges. Of course, it diverges when the ratio goes to something bigger than 1. For crying out loud, that means the terms are growing, which is a horrible situation to find yourself in. Yeah. Well, I don't know if it's horrible, but at least it makes it obvious that the series diverges. Yes. The terms are getting bigger and bigger and bigger. Well, we're going to get divergence, correct? Remember, in order to have a chance to converge, what needs to be happening to the terms? They need to be going to 0, yes? And if they're growing, well, that's a problem, yeah, to that end, okay? And again, we see why the ratio test is necessarily inconclusive when the limit of the ratio of consecutive terms is exactly 1, because we have examples of convergence and divergence where that happens, yes? Any questions before we start doing some examples? Yeah, Daniel. Uh-huh.
In that case, would that case fail the end?
All right, so the question is, in case 2, where the limit of the ratio of consecutive terms is bigger than 1, would that fail the nth term test? Maybe. I could cook up examples where you actually still can get it to go to 0, or at least to get the limit to like not exist or something like that. But in essence, what's happening is what you basically have is a geometric series where the ratio is not smaller than 1, but bigger than 1. Does that make sense? And I guess, oh, well, yeah, I guess that is true. So if it's a geometric series with ratio bigger than 1, because this limit is basically acting like your ratio, okay? Whatever it happens to be. If that ratio is bigger than 1, then yeah, I think that, yes, I believe that in all cases, in the geometric case, you end up with the nth term test essentially failing. Okay, so I think I could make that happen, yeah. So that's a good question. Yes?
So if we were to use the ratio test and it does come out as inconclusive, should we solve the series a different way?
Yes. I mean, that means that you would just have to, right, so if the ratio test is inconclusive, you're going to have to say, well, I'm going to have to bang it on the head with something else, I guess, yeah? And by the way, there do exist cases where the ratio test is inconclusive and the root test is not inconclusive. Does that make sense? So that's why the ratio test is more powerful, or sorry, the root test is more powerful than the ratio test. Okay? But we haven't even talked about the root test yet. I'm just sort of foreshadowing what's coming here. Okay, good questions. Other questions? Let's do some examples. Okay. Yeah, how about this? What about sum? Okay, and I'll let you kind of think about this one together. Sum in going from 1 to infinity of 1 over n factorial of 1 over n factorial. Okay. So think about that one with someone right around you, and we'll kind of reconvene here in just a moment. All right, Jared, I saw you kind of go. Yeah, seems to work. So what'd you do? So what's a sub n? 1 over n factorial, and therefore what's a sub n plus 1? Okay.
So then when you put it in the fraction, they're just going to flip. So you're going to have n factorial over n plus 1 factorial.
Okay, right. So just to prepare what you're, I think I see where you're going with this. So like, how should I write n plus 1 factorial so that cancellation most easily is most obvious? Yeah, so it's n plus 1 times n factorial, basically. Yeah? So then you went like this. An plus 1 over an, right? And I guess we could put absolute values, but you know what I mean. And if you do that, okay, let me just write down what you have here. Divided by 1 over n factorial. What happens to the n factorials? Yeah, those cancel completely, right? And all you're left with is 1 over n plus 1. And then you take the limit as n goes to infinity. Okay? And what happens as n goes to infinity? You get 0. You go, huh? Well, all I needed was for the limit to be less than 1. Well, that's way less than 1, right? That's like 0. It's like as small as it could get. What this means is this thing is like behaving far better than any geometric series. Do you know what I'm saying? Like you're getting a ratio that's so tiny that it might as well be 0. What that basically is telling you is that this 1 over n factorial goes to 0 faster than any exponential function could. Does that make sense? So like 1/2 to the n goes to 0 really fast, but 1 over n factorial, boy, that is just going to 0 like crazy fast. Yeah. Okay. So this is less than 1. So what's the conclusion then, Jared? Right. So you say thus. Let's just write thus. The series converges how? Absolutely, which is sort of stupid in this case, do you understand? Because there's not even any negative terms. Of course it converges absolutely, because they're all positive terms anyways, but we just say it converges absolutely by the ratio test. The end. Okay. Do you guys remember? So here's a little recall. I hope you recall. Do you recall the following? If not, I'm going to write it down right now. What is the limit as n goes to infinity of n to the 1 over n? Do you remember? Huh? That was 1. Yeah. What about the limit as n goes to infinity of n to like the 2 over n? Do you remember? That's like, that was n to the 1 over n squared, right? And therefore, n to the 1 over n times n to the 1 over n as n goes to infinity, that's going to go to 1 times 1 or 1. In fact, isn't it clear that the limit as n goes to infinity of n to the a over n, or a is just some constant, what do you think that's going to go to? 1. Seen a pattern here? Okay. What about the limit as n goes to infinity of Cn, or how about, what if I write it Bn, where B is a constant, to the a over n? Where B is a constant. Well, I could break it up to B into B to the a over n, but constant raised to the a over n, as n goes to infinity, that goes to just B to the 0, which is 1. And then I have n to the a over n, which also goes to 1. Are you seeing a pattern here? Like these things always go to 1, right? So when you have constant times n raised to some constant over n, that limit goes to 1. And we used L'Hopital's rule to do that. We had to like pull the power down. You remember that? Using exponentials and logarithms. And we ended up using L'Hopital's rule. I promise that is going to be important eventually, okay? So I just wanted to get that out there right now. So let's do another example here. Let's see. Yeah, okay, so, right. How about this one? So file those things away in your mind. We'll use those eventually. I just wanted to remind you of that. But here's another example. Sum n going from 1 to infinity. By the way, who cares about where we start, right? I'm just putting something in there. Minus 1 to the n minus 1 times 3/2 to the n, 3/2 to the n, all over n squared. That looks pretty nasty. But what do you guys think about that? Okay, so think about that for a minute. And again, just think about it in the context of the root, or the ratio test, I'm sorry, the ratio test. We still haven't done the root test yet. Okay, so think about that. And let me just to kind of point you in the right general direction. You're going to take absolute values, correct? So what about the -1 to the n-1 stuff? What's going to happen with that? Just goes away. So please, when you see -1 raised to something, just get rid of it right away when you're doing the root and ratio test. Like it's just going to complicate your computation. So get rid of that and only pay attention to the other stuff, okay? Because that's going to vanish anyways because of the absolute values. All right, so work on that for a sec. Well, what do you have for me? Yes, Michael.
So, you just want the answer, or you want how I got there?
Okay, yeah, so what's AN?
So AN is equal to, I have AN equal to 3/2 n over n squared.
Okay, so let's just pretend that that's like absolute. I mean, because you know that taking the absolute values going to get rid of the -1 to the n-1 anyways, right? So the absolute value of this is equal to 3/2 to the n over n squared. So what's the absolute value of an plus 1 then, Michael? Right. And I mean, I don't know. Sometimes I like to prepare things for what looks like is going to happen eventually. You know you're going to put an plus 1 over an, right? When you do the ratio test, you're going to put an plus 1 over an. Therefore, some kind of cancellation is going to happen. So sometimes it's worthwhile to say, well, this is basically like 3/2 to the n times what? Times an additional 3/2, yeah? Over n plus 1 squared. So when you look at the ratio, what happens, Michael?
Then when you, so that is in complex, like you could put the 2 in directly, but it simplifies to 3/2 n plus 1 squared, and then all over n squared.
Okay, right. So, oh wait.
Once you do the division. So I had 3/2 n plus 1 over n squared, and then that whole thing was over 3/2 to the n over over n plus 1 squared, and then that whole thing was over 3/2 to the n over n squared. That's the full ratio.
Okay, well, okay, so hang on a sec. So 3/2 to the n, 3/2, and this thing is divided by n plus 1 squared, right? And that's divided by 3/2 to the n over n squared, yeah? Because that n's below. So you got so you're saying, look, this junk right here cancels, right? And the 1 over n squared flips upstairs to be attached to the 3/2, yes? So then it's going to be 3/2 n squared divided by what?
Divided by n plus 1 squared.
Yeah, that's right. And so when I take this limit, what do I get?
Well, the way I figured it out is I separated the 3/2 out, and then I just had n plus 1 over n quantity squared, which then just goes to 1.
So you keep saying n plus 1 over n quantity.
Oh, sorry, I did it backwards in my word. N over n plus 1.
Okay, n over n plus 1 quantity squared, right? Yeah. So, okay, so then it's right, then 3/2, that ratio of the n stuff goes to 1, yes? So the 3/2 stays where it is. So in the end, you get 3/2, which is greater than 1. So what's the conclusion? So, right, so the series does what? Diverges by the ratio test. And is that really very surprising? Because think about it. We had 3/2 to the n. Do you know what I'm saying? Look at that series. I mean, so you have an exponential thing that's bigger than 1. Do you think that that n squared is going to be enough to offset that? No. The terms don't even go to 0 here, okay? I mean, if you actually just applied the nth term test, you would have ended up with a diverging series, because the terms themselves, like forget about the -1 to the n minus 1, you have 3/2 to the n over n squared. If you computed that limit, what would you get? 3/2 to the n. Remember, exponential always grows faster than the polynomial, yeah? In this case, the ratio is bigger than 1. That thing's going to be growing. So is n squared. It's of the form infinity over infinity, but you know the exponential whips the polynomial, yeah? Therefore, these terms go to where? Infinity. The terms go to infinity. Therefore, clearly, what happens to the series? Diverges. But the ratio test detected that automatically. Do you know what I'm saying? The ratio test just went whoop. Yeah, here you go. Diverges, right? But the nth term test would have done the job as well, okay, even if we didn't have the ratio test necessarily. All right? But I want you to just have intuition about this. When I look at that, I say 3/2 to the n over n squared. Well, good grief, 3/2 to the n is just going to destroy n squared, yes, in terms of its growth. Therefore, the terms, the individual summands, are not going to go to 0, which means I have no chance of what? Converging. Okay, so that's what the term test says. So we must have divergence here. Any questions on that? Any questions? Let me see. I think I want to do one more, but I'm going to do this together with you, okay? So let's do this. Okay? Sum. Who cares where it starts, okay? Who cares? Sum of what? I'm going to go -1 to the n, 2 to the 4n, over 2n plus 1 factorial. Huh. Okay. Yeah. Now, let's first, for a minute, just talk about growth rates. So upstairs, I basically have 2 to the 4n. Does that make sense? That is essentially like 2 to the 4th all raised to the n. Okay, which is what? What's 2 to the 4th? Let's just be honest. That's 16. So the top is basically growing like 16 to the n. And on the bottom, I have a factorial. Okay? So I have two competing infinities here. One of them is an exponentially growing thing. The other thing is a factorial growing thing. Who wins? Factorial by a landslide. Therefore, these terms are diving to 0 very fast. Yeah? So what do you suspect is going to happen immediately before we do anything at all? You suspect it's going to converge. Does that make sense? That is the suspicion. And incidentally, I'm going to use the ratio test here, but, and I have the -1 to the n. And by the way, in the last problem, we had divergence. I didn't have to say anything about absolute anything, right? Because it diverged. But in this case, I have the -1 to the n. That's not going to end up mattering. So we actually suspect that not only does this thing converge, but it converges how? Absolutely. Okay, and let's sort of apply the ratio test to make that rigorous. So first of all, what is the absolute value of an here? Absolute value of an equals, okay, the reason I put absolute values around it is I'm trying to get rid of the -1 stuff right away. That's going to be 2 to the 4n over 2n plus 1 factorial. And then we're going to prepare ourselves for the next term. And remember, we replace n with n plus 1, correct? And if I replace n, right, if I were to replace this n right here with n plus 1, if I put an n plus 1 right here, and I put an n plus 1 right here, do you guys realize that, if I put an n plus 1 in both of those places, do you guys realize I'm going to have to distribute the 4 in the one case and the 2 in the other case? Yes? So watch what happens. Okay? 4 distributed n plus 1 gives me a 2 to the 4n plus what? 4. Basically, I just distributed the 4 to n plus 1. And downstairs, I have to distribute 2 to the 2 times n plus 1. And what's that going to make? 2n plus 2 plus 1, right? 2n plus 2 plus 1, which is 2n plus. Make sense? And then what I do is I stare at an and I say, okay, essentially I just have an extra, I have 4 extra 2s. Yes? Okay, so let me just kind of, let's think about this carefully, okay? So what about this guy right here? What about the factorial? 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 factorial, yeah? So this is 2n plus 3 times 2n plus 2 times, and believe me, this is a good preliminary legwork here. And what about the top right here? What about this top? What is that? And I want to kind of think about it in terms of what was true about an. What is that? That's 2 to the 4n times 2 to the what? You see what I'm saying? So let's look at the ratio. Hey, lots of stuff is going to cancel. For instance, the 2 to the 4n's are going to cancel, right? And what else? 2 to the 4n's are going to cancel. And what else is going to cancel? 2n plus 1 factorial. Okay? So what am I going to end up with here? Help me out. Remember, I have a fraction over a fraction. I have a fraction over a fraction. An plus 1, there's going to be 2 surviving factors like 2n plus 3 and 2n plus 2. And then you have to remember that from an plus 1, I'm going to have 2 to the 4th left. Does that make sense? And you have to get these things right. You have to have them in the right place in the numerator and denominator, or else you're going to really screw it up. Does that make sense? I mean, you just need to make sure that things are in the right spots. So I'm telling you, when you do this cancellation, this is what ends up surviving. And what happens to this as n goes to infinity? It goes to 0, which is clearly less than 1. So what do I conclude about this? Yeah, so the series converges absolutely. By what? By the ratio test. Okay? Be very careful about your cancellation. This is a place where you simply can't afford to make any arithmetic errors at all. You make an error, you end up with an n in a numerator when it should be in the denominator. That will ruin everything, yes? That's one reason it's good to have intuition from the beginning about whether a series converges or diverges. That's why at the beginning we said, oh yeah, this thing basically is going to converge absolutely. But the ratio test makes that rigorous. All right? That's it.